Okay, so welcome everyone to this last session of today. Our next speaker is Marina Nicolini from Universidad Nacional de Córdoba. She's going to talk about the classification of ERP G2 structures on lead groups.
Thank you very much, Viviana, and thank you to the organizers. Thank you, Caroline, Romina, and Ramiro for giving this opportunity. And as Viviana said, I'm going to talk about ERP G2 structures only groups. And this is a joint work with my advisor, Jorge Lauret. This was part of my PhD thesis. So to start, I would like to give a motivation of why people study G2 structures. So as you all must know, in 1955, Berger classified all the possible holonomy groups that a simply connected irreducible Riemannian manifold could have. And this was a list. And in particular, it appeared the Lie group G2, the simple exceptional Lie group G2. But at that moment, there were not known examples of Riemannian manifolds with holonomy containing G2. So, the timer, okay. So in a few years later, Bryant proved the existence of local examples in 1987. And 2 years later, in a joint work with Salomon, they found complete examples. And in 1995, 40 years from Berger's classification, Joyce proved the existence of compact examples, but there were not known concrete compact examples. And that's how appear G2 structures. G2 structures appear as a tool to construct Riemannian manifolds with holonomy containing G2. And to define what is a G2 structure, we are going to set a differentiable manifold M of dimension 7. And this is differentiable only, not Riemannian. And the G2 structure is going to be a differentiable free form on M that I'm going to name phi, such that at each point, this G2 structure is positive. And what does positive means? It means that it can be written as this free form, where E sub 1 until E sub 7 is the basis of the tangent plane, and E supra ijk is denoting the wedge product of one forms. Okay, so I set the name positive, which is a really nice name, but this definition, it's not that nice. But the thing is that the name positive, it's because every G2 structure uniquely determines a Riemannian metric and a volume form. So in particular, if you have differentiable manifold M and you have a G2 structure on M, you are going to have a Riemannian manifold structure, okay? So also, if you have a Riemannian metric and a volume form, you have a Laplace, a Hodge star operator, and having a Hodge star operator implies that you have the torsion forms of a G2 structure, okay? The torsion forms of phi are defined by, these 0, 1, 2, and 3 forms on M, and they are determined by the differential of phi and the codifferential of phi. So what has to do this with holonomy? And the thing is that when M is compact and the G2 structure is torsion free, it means that all the torsions vanish. Then the holonomy of the Riemannian manifold M with the metric G phi is containing G2. So G2 structures are a tool to construct holonomy G2 manifolds. I'm not going to lie to you, I don't know anything about holonomy, but people said that constructing torsion-free G2 structures is not easy. And that's why it's very common that people study or closed G2 structure or co-closed G2 structures. In particular, we are going to study closed G2 structures, meaning that all the torsion tau 0, tau 1, and tau 3 vanish, and so the only surviving torsion form is the 2 form tau 2. Okay, so I finished with the motivation here with why people study G2 structure, and we are going to study closed G2 structures, okay? And the title of this talk had another word, ERP, and I'm going to define it in this slide. So I said before that when phi is closed, and we are going to work with closed phi, the torsion form that survives is the 2 form tau that I'm going to name only tau, because there is no other torsion form, not 0. And Bryant proved this theorem that says that when the differentiable manifold is compact and the G2 structure is closed, then this inequality holds for the scalar curvature and the Ricci curvature of the metric defined by G. Okay, note that here there is a 3. We know this inequality with a 7 instead of 3 by Cauchy-Schwarz, and Bryant proved it for the number 3, okay? And this inequality, he named it the Ricci pinching estimate, and he proved that the equality holds if and only if the differential of the torsion depends quadratically on the torsion in this way. And so if this inequality is called the Ricci pinching estimate, the G2 structures that satisfy this condition are going to be called extremely Ricci pinch. And we are going to forget about the compact assumption. In general, we are going to define a closed G2 structure to be extremely Ricci pinch or ERP if it satisfies this equation. And of course, defining things, it's free, so you can define wherever you want, but the definition is only interesting if there is at least one example. So the first question is, are there examples? And of course, the first known example was given by Bryant, and he gave an example of an ERP G2 structure on this homogeneous. I am using the, can you see the hand?
Yes.
Okay.
Yes.
Thank you very much. Okay, so he gave the ERP G2 structure on this homogeneous presentation, and Clayton and Ivanov proved that this is equivalent to an ERP G2 structure on a non-unimodular solvable Lie group. And the second example was given by Jorge, and he found an example of an ERP G2 structure on an unimodular solvable Lie group. So of course, these two examples are non-equivalent. And the first question that we asked ourselves was, are there more examples or what happened here? Because Bryant in this paper, he proved a lot of nice things, a lot of nice results for ERP G2 structures. And so why are there not more examples? And since we have these two examples and we have them on Lie groups, we can study the problem of finding more examples on the Lie group situation. So if we set G a Lie group, we are going to consider a Lie group G instead of a differentiable manifold M with a Lie algebra with basis C1 until E7. And of course, there is this correspondence between left-invariant G2 structures on the Lie group and positive 3 forms on the Lie algebra. Because since this is a Lie group, it only matters what's happening at the identity. And so all the equations that we have are going to we are going to need them only on the Lie algebra level. So the first thing that I want to remember is that being that phi is positive, it means that we can write phi as I told you on the second slide. But here I wrote something different. I took the term E347, and on the other 6 terms, I separate everything that has 7, 3, or 4 from that what has not. And it remains like wedge product between forms on the vector space generated by 3, 4, and 7, and the vector space generated by 1, 2, 5, and 6. So I gave names to these 2 forms, and these names are not relevant now, but it's a notation that I'm going to use after that. So I put the name omega 7 to this 2 form on the on 1, 2, 5, 6. That is partner of E7, omega 3, the partner of E3, omega 4, the partner of E4, and of course it remains the 347. And okay, if we are studying the problem of being an ERP G2-structure on a Lie group, we still need that phi must be closed. We still need phi to be closed. And this condition is now the exterior derivative of phi equals to 0, but this is a 4 form on the Lie algebra. And the same for the ERP condition is the same equation, but now we are referring at the 3 form on the Lie algebra. And the new thing here is that we can consider an equivalence relationship that it was very useful to us. And we are going to say that 2 different G2-structures on 2 different Lie groups are going to be equivariantly equivalent if there exists an isomorphism on the Lie groups instead of a diffeomorphism, such that preserves the G2-structure, okay? So, of course, if 2 G2-structures are equivariantly equivalent, they are going to be equivalent. And with this in mind, we were looking for examples, but it was very hard to know if 2 examples, once we got 1 example, it was very hard to know when it was equivalent to the examples that we already have. And so looking for examples, we could prove this first structure theorem that it's not nice, it's pretty technical, but I'm going to explain a little bit better in the next slide, so don't panic. We proved that every left-invariant ERP G2-structure is equivariantly equivalent, so there exists an isomorphism up to scaling to G phi, where G is a Lie group and phi is the same phi as before, okay? And such that the torsion form is fixed. So we have a basis that we can choose phi as before, and we can fix the torsion form. And these conditions also satisfy. It's okay, I'm not going to stop here, but the only thing I wanted to say that I explain here is that it's going to appear this theta, and this theta is the derivative of the, is the representation that is derivative of the action of the linear general group. And here it's better explained. And okay, so let's go to what does the proposition say, the theorem says that given an ERP G2-structure on a Lie group G, we can assume that the.
Sorry, Marina, can you go back to the previous slide?
Yes, it's not nice.
Yes, so no, you don't say that your theorem is not nice. That, so is it So G0 is an almost abelian, right?
I'm going to explain it here.
Okay, you're gonna say okay.
Yes,
yeah, go
yes.
ahead.
Okay, after I finish this slide, I ask you again. Okay, so summarizing, the theorem says that given an ERP G2 structure on a Lie group, we can assume that the G2 structure is the same as before with the omegas now. The torsion form has this form, and the Lie algebra has this structure of a semi-direct group, a semi-direct algebra product, I'm sorry, and where G0 has this basis 7, 3, 4, G1 has basis 1, 2, 5, 6, and this 1, 2, 5, 6 is an abelian ideal of G, and 3 and 4 is an abelian ideal of G0. So the Lie bracket is given by the adjoints of E7 restricted to 3 and 4, because it's an abelian, it's ideal of this 3-dimensional space. And the adjoint of 7, 3, and 4 restricted to G1. So these are 4 matrices that I named A1, this is 2 by 2, A, B, and C, these are 4 by 4. That is concerning to the Lie algebra structure. Is that okay, Ramiro?
Yeah, no, I was going to ask if the Bryant's example was one of these, and it clearly is, right? Because when this is like when you take a representation, I mean, of this Lie algebra, the algebra is a subalgebra of SL2C, and then when the representation is a restriction of an SL2C representation, then you get a particularly nice example. But yeah, of course, you know this already. So sorry.
But it has this structure. We can assume this for every ERP G2 structure on a Lie group. So since Bryant's example is equivalent to an example on a Lie group, it has this structure. It can have this structure. I'm going to write Bryant's example with this structure after this in a 3. But okay. Okay, so this is the Lie algebra structure. And since we have to phi is ERP, then there are some other equations that A1, A, B, and C must satisfy. The first one is that these equations are implied by the closed condition. And there is this other equation that is implied by the ERP condition that now is linear because we have fixed tau. And we cannot forget about the Jacobi condition that this is quadratic and it's not nice at all. But these are the things that we have to that have to be satisfied for A, B, and C, and A1 in order to be an ERP G2 structure. Note that from these first 3 equations, A, B, and C are traceless. It's not so easy to see like this, but they are traceless. So all the unimodularity of the Lie algebra is codified in the trace of A1. So G is unimodular if and only if the trace of A1 is 0. And I don't want, the first 2 corollaries of this theorem are pretty nice, and we prove that every left-invariant ERP G2 structure is a steady Laplacian soliton. It means that it satisfies this equation for the Laplacian operator, and this is the Lie derivative. And it's also an expanding Ricci soliton, so it satisfies this equation. And the second corollary is that every non-unimodular left-invariant ERP G2 structure is exact. And why do we have to ask non-unimodular? Because we can write the G2 structure as the derivative of these two forms, and here it is involved the trace, the inverse of the trace of A1, so it cannot be 0. And okay, this is the ingredients we use in the proof, and it's a very technical proof because it's a very technical theorem, but mostly we use some of the properties that Bryant proved for the torsion of an ERP G2 structure. We prove also that we use also that the Ricci has this form, the Ricci operator, and it's negative and 0 eigenvalues. And also that the equivariant equivalence in both cases, unimodular and non-unimodular, are given by these two Lie groups. So I'm not going to stop here, but the important thing here is that we have, that, see, by the 4 item, the Lie algebra cannot be nilpotent. And also, since 1, 2, 5, 6 is an abelian ideal, then the new radical must have dimension at least 4. So there are 3 options for the dimension of the new radical. It can have dimension 4, 5, or 6. Lauret examples is the unimodular example. It has dimension 4. And I wrote it here in the ABC notation. And in this case, Fino and Rafero proved that if you have a left-invariant unimodular ERP G2 structure, then the Lie algebra must be isomorphic to mu j. This is the Lie algebra mu j. But it does not imply that there not could be another ERP. I mean, they proved this, and it's a very interesting result, and we use it, but it might be another ERP G2 structure on the Lie group that it's not equivalent to the G2 structure given by Lauret. But we could not have another new example in this case. The second case is that the Lie group is non-unimodular and the new radical has dimension 5. And in this case, there were not known examples, and we find 2 examples. I present here the Lie algebras in the format A1, A, B, and C. These examples are not, these Lie algebras are not isomorphic because the new radical of M2 is 3-step nilpotent, I think, and this one is 2-step nilpotent. So they are not isomorphic. And in the third case is the case where the new radical has dimension 6. In this case, there was only one example, the one given by Robert Bryant, and in this format A1, A, B, and C, the matrices has this form, and Fino and Rafero proved that this is also a family of ERP G2 structures, but note here that, for instance, B and C are the same matrix, and also the A's are very similar. The thing is here that we proved this result, that if you sum a derivation of the 6-dimensional Lie algebra to the A1A, then you obtain an equivalent ERP structure. So these examples are not isomorphic, so they are not equivariantly equivalent, but they are equivalent. Okay, and in this case, we also find another example. It's not really nice comparing to Bryant's example, but remember that we have a nice G2 structure and a nice torsion form. So we cannot have everything. And this is not equivalent to the other examples because also the dimension of the new radical is different from them. And okay, so there were only 2 examples. We find 3 more examples. And in total, we have five non-equivalent examples. And we could prove this classification theorem. And the proof of this theorem was separating and treating each of the three cases in separate ways. And we proved that every left-invariant ERP G2 structure is equivalent to one of the five examples I mentioned above. So this is the Bryant example, the Lauret examples, in the three new examples that we found. And also, if you want a classification up to equivariant equivalence, you only have to add the examples given by Fino and Rafero. Remember that these examples are equivalent to Bryant's example. And this result is pretty interesting because Gavin Ball studied what happened in the homogeneous case. And in the homogeneous case, Gavin proved also in his thesis that every closed homogeneous ERP G2 structure must be equivalent to one of the following examples. And there were only the five examples that we proved in our theorem. And in this paper of Gavin, he found this homogeneous presentation of M2 and M3. And these presentations allows him to find more symmetries on these Lie groups, so they are pretty interesting. And also, I think I have time, so I didn't write anything, but I want to tell you that since Bryant gave this example as a homogeneous space, and from that presentation, it admits a compact quotient. So we have, there was only one example of a compact ERP G2 structure, but last year, I think, last year, Jorge Lauret, in a joint work with Ines Kath, they found the lattice on this unimodular example, the only unimodular example. And so it admits a compact quotient. And from this presentation of M3, Gavin Ball found another compact ERP G2 structure from this presentation. So there are three non-equivalent examples of compact ERP G2 structures. I think there is nothing known about M1 and M2. M1, remember, was the not pretty nice one. And okay, that's all. Thank you for your attention.
Thank you, Marina. Is there any question or comment?
I have one small question. Can you say anything more about the compact example of Gavin Ball? Or
I can't, but maybe Jorge can. Something more about like what?
Maybe I cannot.
I don't understand the question, I think.
I think he found, lattices in this G. I'm pointing and you're not watching. G over S1, he found lattices on these groups.
Okay.
On these Lie.
Yes.
Yes.
Which is unimodular.
Mm-hmm. Okay, thank you.
Further questions?
So Marina, how do you prove non-equivalence between these structures?
between
not from the Lie theory, like from the G2 point of view. How do you prove they're not equivalent?
They are all completely solvable, so they are not isomorphic, and this implies that they are not equivalent, right? That was the question.
Yes, I don't know how do you test equivalence in the G2 setup, so that's why I ask.
Is it up to isometry? Because I had the same question.
It's a diffeomorphism that preserves the G2 structures. That with you have to act the action. I don't know if there is. It's the only action that I work with.
Yeah, no, that's correct. Yeah, but in practice, like, what do you have to? Do you prove that they are not isometric? But is that enough? That they are not isometric? Yeah. Okay. If they will be equivalent G2 structures, then the metrics will be isometric, I guess. Okay.
Exactly.
Okay. The other way around doesn't work. Yeah. Okay. Sorry, my bad. Yeah. Thanks.
No, thank you.
So, is there any other question? If not, let's thank Marina again. Thank you for the beautiful talk.
Thank you.